I'm going to now try and condense that into 15 or 25 slides and present it in 15 minutes. So I have a space for questions and answers at the end. I'm not sure that we're going to have time to do that. I'm here all day over on the masonry fixing stand, so if anybody wishes to ask questions in more detail, feel free to do that. So basically, steel to concrete connections. At the start of the project, the design engineers will have to decide how they're going to connect steel to concrete. There's cast-in systems, cast-in headed studs, cast-in channels, there's holding down bolts in cone boxes, or alternatively there's what we call post-fix systems, which are expansion anchors or resin anchors which go into drill holes in the cured concrete. So I'm going to basically walk you through the different systems. First of all, on a project, when an engineer is faced with bolting steel to concrete, he has to decide how he's going to do that and all of the implications of making, say, a cast-in system. If you're going to use a cast-in system, there has to be a lot of coordination between the concrete, guys pouring the concrete, and the guys arriving with the steelwork later on, which might be several weeks or months later on. So it's quite a difficult task, perhaps, to coordinate that. It's not always possible, in which case maybe post-fix systems are much handier. The typical applications that exist on the market, or the typical applications where you'd use the product, are basically bolting steel beams into concrete walls, facade subframes, bolting steel beams onto concrete beams, crowd control in stadia, so crowd control barriers, seating, all that sort of stuff, jet fans and ventilation systems in road tunnels, bracketry for carrying mechanical and electrical systems in rail tunnels, cranes and robots in factories been fixed to the floor, edge protection, be it on a staircase or on a bridge or on a balcony, and also other sorts of protection where you may have, in this case, scaffolding being protected from vehicles, but you may have in shopping centres and car parks particular barriers for protecting other elements on the project. So the products that are used typically, you've got the first item would be a headed stud welded to a plate, and as you can see, these products are primarily bespoke products for particular applications on site. There's very few proprietary manufacturers of this type of system. The problem that brings is that when you decide you're going to use this system, it's used quite a lot in the States, it's not used that much in Europe. When you're going to weld on headed studs onto the back of a plate and you're going to cast it into the wet concrete, the profile, in this case a square box section, might be welded onto the plate at the time of casting in, or it may be something that you do at a later stage where you come along and you weld on your profile onto your plate. The problem is when you have to verify the capacity of that connection, you have to be able to provide proof as to the concrete capacity for the particular system that you have. And there's very few people, fabricators, who would be fabricating stuff like this, who have the ability to actually work out the concrete capacity from the Eurocodes. Hence, it's not that popular here. Male thread cast-in headed studs, or holding down bolts as people like to call them. These are typically headed studs or maybe hexagonal headed bolts which have a male thread on the end of them. There may be some sort of a frame system or a template at the top to keep the spacing between the anchors when it's cast into the wet concrete. Alternatively, you have the system which you saw earlier on where you have a cone box which allows for a little bit of lateral movement of the fixing, so that when you do come to connect your steel element, you can actually move the anchors ever so slightly. It gives you a little bit of tolerance. When these are installed, and when the concrete has cured, and when they're subjected to tensile loads, the concrete, this yellow prism or cone of concrete, has to resist the actions that are applied to the column. And it's important to realise how to calculate that capacity and not just the capacity of the bolt. Female threaded cast-in studs, again, they're very similar. They're a cast-in stud with some sort of a socket or a coupler on the top of it, and these again are cast into the wet concrete. Again, a template of some sort may be used at the surface to keep the anchor spacings as it should be, so they don't move around while the concrete's being vibrated. Typically bolted onto the back of a piece of formwork or a shutter. And cast-in channels. Cast-in channels come in a whole range of profiles, different sizes, different shapes, and they have a T-head bolt which engages in the channel afterwards. Again, as you can see, they're set into the wet concrete. They can actually be tied into the reinforcement, so you can get an additional positive influence from the strength by attaching it to the reinforcement. The important thing is that when the concrete is poured, the face of the channel is flush with the face of the concrete. This isn't that popular quite often they'll be on the vertical face and they'll be nailed onto the back of the formwork. So when the formwork is taken down, the channel is visible. The channel will have some sort of foam or polystyrene infill to prevent concrete ingress into the channel, which obviously would foul the T-head bolt. So what happens is when you strike your shutter and you're left with your channel in the face of the slab, as is in this case, you then can take out the foam or the polystyrene, place in your T-head bolt, turn it to 90 degrees, and now you have a very positive connection for cast-in channel. The other systems then are mechanical post-fix systems. This is my area of expertise. This is where I've been working for 25 years. Basically, they go into hardened concrete. They don't go in, they're not casting into wet concrete. You drill a hole, you insert the anchor into the hole, and then you torque the anchor. The anchors in the AOTA document are referred to as torque-controlled expansion anchors. They have to be torqued with a calibrated torque wrench. They can't just be hammered in willy-nilly and tightened with a spanner. Also on post-fix systems, we have resin or chemical systems. Chemical systems come in a variety of forms. You can get them in a capsule form, or you can get them in an injection resin form. In the capsule form, you drill the hole in the concrete, and you clean out the drill dust out of the hole, and then you pop in the capsule and you spin in the threaded component on rotary and hammer action to mix the two components that are inside in the capsule. When they're fully mixed, and when the curing time has elapsed, you can then connect to the anchor stud. The injection resin systems come in a cartridge. What I don't show on the slide here is there's a nozzle that goes onto that cartridge, which has a static mixer, like a worm inside in the nozzle. As the two components are extracted from the cartridges, they mix in the nozzle, and the material that comes out the tip of the nozzle is a fully mixed resin. It's injected into a cleaned out drill hole, and then the anchor stud is just simply twisted in by hand. So, old system. When I'm talking about old system, I'm talking about typical technical information that existed prior to the European standards and codes. So that's a typical extract from a document, a manufacturer's document for a holding down bolt. They don't give anything about the capacity, they just give the dimensions of the product. And what the designer would have to do is he'd simply look at the dimensions from the table and he'd work out the steel capacity of the bolt. So he'd be able to calculate very simply what an M16 8.8 grade bolt can resist. And if he has 4 of them, then he has 4 times that capacity. There was no consideration for concrete or the concrete capacity. On cast-in female threaded studs, again that's typical from a manufacturer, and you can see here an M12 can resist 500 kgs or 5 kilonewtons approximately. So if you have something that requires 20 kilonewtons, use 4 of them in a particular formation. But again, there was no reference to the concrete capacity or the concrete strength. You just simply took the value from the table. Cast-in channels, again, that's a typical extract from one of the major manufacturers. And you can see here there's different channel profiles, and then there's different T-head bolts that go into those profiles. So if you have a 40/25 channel, which is the profile of the channel, and you have a 12mm threaded stud, you have a recommended load of 8 kilonewtons. All of these recommended loads were based on serviceability limit state, not on ultimate limit state. The new design models all work off ultimate limit state, or factored loads, for want of an easier description. And again, you just simply took the value from the table. On anchors, again, that's a typical extract from an anchor handbook. And what you would do is you would take the value from the table. So if we've got 25 Newton concrete and we've got an M12, that has a recommended load of 9 kilonewtons. They then had additional tables included in these manuals, whereby for anchors close together or close to an edge, you take a reduction factor and you apply it to that 9 kilonewtons. Many people were doing that and happy to do it, not fully understanding why that was happening. The reason that was happening was the anchors weren't getting weaker when you were putting them closer together. The concrete substrate into which they were fixed, you were now employing less of that concrete, and the concrete capacity was less. So these graphs alluded to concrete capacity, but nobody actually fully understood what was happening. Sometimes you would have a positive factor for concrete strength. In this particular case, they show different concrete strengths and different values. Some of the tables might just have for 25 Newton concrete and then give a positive influence for 35 or 45. So very little about the concrete condition, the strength or the reinforcement was either required or considered when working out the capacity for a connection. Concrete, however, behaves quite strange. When it's loaded, it'll deflect. Obviously that is grossly exaggerated, but it's there to show that if the forces come on the top of the concrete has been pressed together, it's in compression. The underside of the concrete has been torn apart, it's in tension. That's where your reinforcement goes, because reinforcement is fantastic in tension, it's not great in compression. Concrete is the reverse. Now, if you can imagine locating an anchor in the top of this slab here, an expansion anchor, a post-installed expansion anchor, and the concrete is pressing in against that anchor when the concrete element is loaded, that will actually help to increase the capacity of the anchor. Inversely, if you're on the underside of the slab, in this case, and you're in the tension zone of the concrete, you're in what is called cracked concrete in the European standards. When we speak to people about cracked concrete, they get quite excited and they think there's something wrong, that the concrete's broken or damaged in some way. It's actually tension zones is what's been discussed and talked about. So obviously, depending on where you install the anchor, that will have an influence on the capacity of the product. Whoops, go back. So the capacity of a steel to concrete connection is vastly dependent on the strength and condition, and by condition I mean cracked or non-cracked, of the concrete base material. Most connection capacities are determined by the concrete capacity. And certainly when you have one or more anchor or bolt employed in a connection, concrete capacity will almost always be decisive. So here are some typical failure modes showing how the concrete behaves. So if you test anchors to ultimate loads, this is the type of thing that will happen. The concrete will crack, or cones will break, or the concrete will split. So for this reason, the concrete design capacity was developed. This started back in '97. It involved the use of European technical assessments, or it founds the basis of European technical assessments and European technical assessments, which, as you all know, and as Yvonne alluded to, is to do with CE marking on the product. It has now at this stage incorporated the cast-in systems as well, which were sort of left in the cold until now. The resistance capacity of any product used in steel to concrete connections depends on the environment in which it's placed. So you can't ask me what's the capacity of my M12 true bolt. You have to tell me where it's being used and what the conditions of the concrete are. The resistance capacity could be determined by the steel capacity of the fastener, but it's more likely to be determined by the capacity of the concrete locally. With the arrival of Eurocodes, we now have CEN 19924. It's in its final draft form. I don't think it's going to change much. The document now has 5 parts to it. It's called the Design of Fasteners for Use in Concrete. Part 1 is anchors in general. Part 2 is headed fasteners, cast-in headed fasteners. Part 3 is anchor channels. 4 is post-fixed mechanical anchors, and 5 is post-fixed chemical anchors. That's basically part 1, which tells you everything you need to know about the different types of systems. Part 2 then talks about headed fasteners. And within headed fasteners, you have to then determine for each anchor.
And Freedom Divine from the National Children's Hospital, please make their way to the construction main stage. Thank you.
Okay, you have to verify the capacity of the anchor. You have to check the steel failure in tension. You have to check the pull-out failure, the concrete cone failure, the splitting failure, the blowout failure, the steel failure of reinforcement, and anchorage failure of reinforcement. Within the document, it gives you lots of graphics and formulas for calculating the concrete capacity. In those formulas, you have to tell it whether the concrete is cracked or non-cracked, what the reinforcement is like, whether you have edge distance or anchor spacings. And from the anchor's perspective, you need to know the embedment depth, the diameter of the anchor, and the steel grade. That's for tension. If you then take a headed fastener in shear, you have 6 different proofs that you have to check for shear. When you check all of these proofs, obviously the one with the least capacity becomes decisive, and that's the one you use for the capacity of the connection. Again, on shear, it gives all the graphics and it gives all the formulas to do that. Part 3 then is anchor channels, very same thing. There's 11 proofs, quite complex. You can see all the graphics on the bottom where you have to prove what the anchor channel will do, and then you find the one with the least capacity, and that's the one that becomes decisive. Anchor channels in shear, again, there are 7 proofs, and you have to prove every single one of them, and the one with the least capacity becomes decisive. Then you're into mechanical anchors, post-fixed systems. There are 4 different checks that have to be checked. For any of you that are familiar with ETAG 001 Annex C, the design of post-fixed anchors in concrete, you'll recognise those different proofs because they're absolutely identical. For post-fixed mechanical anchors in shear, again, it's identical to IOTA ETAG 001 Annex C. Then for chemical anchors, again, chemical anchors are different slightly because you have this additional failure model here, which is a failure between, it's a combined failure between cone failure and bond failure. So you're getting some cone failure at the surface of the mouth of the drill hole, and you're getting bond failure further down. And then for chemical anchors in shear, again, there's 4 different failure models. And again, just to verify that steel failure without a lever arm is steel failure in pure shear. Steel failure with a lever arm is when you have shims or grouts underneath the base plate. This now takes the shear load and it converts it into a shear with a lever arm or a bending. So the anchor's capacity is dramatically reduced when you apply a bending moment to the product. These 2 checks have to be checked if and when there's any sort of shimming underneath the base plate. If there's no shimming...
Ventusky and Field Devine will now be beginning their talk in the Main Street construction segment.
Okay, additional information on this stuff, guys, is available. You can buy different publications on it, or alternatively, if you're really interested, I'd recommend you get yourself to Stuttgart in September. Stuttgart University is the hub of anchor design and concrete capacity design models. There's a gentleman called Professor Rolf Ehlergehausen who has devoted his life to steel to concrete connections, and it's his work that's in all of the EN 1992 and the ACI, the American concrete capacity codes. All right, try to cram that into 15 minutes. Thank you very much. Any questions, or have I time for questions? Yeah, okay, where to find me? Masonry Fixings, we've got a big box hanging out the ceiling. You can't really miss us from any place in the hall. I'm around for the afternoon. I'm probably going to have a sandwich now, so you won't catch me for about 20 minutes, but I'm there for the afternoon. Thank you.
Thank you very much, Bryan.